So let's go to the first problem. So let's make the transition. Let us go to the first problem. Oh, I'm sorry. This is frozen. Oh, let me unfreeze it. Okay. Regarding the first problem, what do we have to do? We need to find what are we supposed to find? The domain. So, what's our first step in finding the domain? So, what would be a first step for finding the domain, at least algebraically? So, algebraically, yeah. Oh, yeah. I'm over here. Who did not get a hand up? Anyone else not get? All right. My apologies for that. Let me know if you have any hand up. All right. So, what do you mean? Let me see if I can zoom in so you guys can see better. Algebraically. All right. So step one, algebraically. What would be our first step when we're trying to find a domain here? What are we looking for? Yeah. So, but first I'd say first we need to find our domain restrictions. If you're looking for the domain, by the domain's all real numbers, or you find your domain restrictions. You find your domain restrictions. So I'd say your step is to find domain restrictions. Oh, let me plug in. So the square root of x plus 3, you can't take the square root of a negative. The square root of x plus 3, you cannot take the square root of a negative. So from the square root of x plus 3, you can't take an even root of a negative. So you can't take an even root of a negative. And for the denominator, and for x squared plus 10x plus 24, so I'll draw an area here. For x squared plus 10x plus 24, we need to factor, all right, and then know that the denominator can never be equal to 0. The denominator cannot equal 0. The denominator cannot equal 0. All right? So let's break this down. All right? Let's look at the square root of x plus 3 to find one district. For the square root of x plus 3, if the term under the square root has to be positive, has to be greater than equal, has to be not negative. I kind of gave it away there. What does it have to be? Right? So how do we set this up algebraically? Plus x what? Right? Excellent, Graham. All right. Also, I like the link in your IG. Yeah, right?
Hey, did you follow me? Come on.
When you graduate.
X is greater than you're gonna follow me.
If you want me to. If you don't want me to, I mean.
I want you to follow me.
Okay, x is greater than or equal to -3. Okay, so that's one restriction. So that's restriction 1. Okay, now we need to find the x has to be greater than or equal to -3. So that's restriction, because that means if x is any value that's less than -3, x cannot be that. So x is restricted. Let's look at our other restrictions. Let's first also factor x squared plus 10x plus 24. What is it? What would this factor into? X plus 4 and x plus 6. What's 6 plus 4? 6 plus 4 is 10, and 6 times 4 is? Excellent. So that's how that factors. X plus 4, x plus 6. So that means that x plus 4, denominator can't equal 0. So to find our restrictions, we set our factors equal to 0 in the denominator. X plus 4 equals 0. X plus 6 equals 0. Subtract 4, subtract 6. X is equal to -4. X is equal to -6. Now these are vertical asymptotes. These are the equations of our vertical asymptotes because they don't cancel out. And vertical asymptotes are domain restrictions. But if you have a vertical asymptote, that's a value that x cannot be. So x cannot equal -4 and x cannot equal -6. So now I have all of these restrictions. How do I figure out what my domain is? Think of this like the allergy table. You have to be the most restrictive for the foods at the allergy table. If I have a table, right, and on the table I have a student that's allergic to peanuts, a student that's allergic to apples, and fish, and the student that is allergic to fish. All right, I have to be the most restrictive for the foods that to be on that table. If you just don't bring peanuts, peanut kids don't get sick when it's just allergy table. If you make sure you restrict peanuts and apples, but someone's bringing over a big old trout or a big old bass, right? This kid's gonna break out in hives. Okay. So you have to be the most restrictive. Here, x is greater than or equal to -3. Completely x cannot equal -4 and x cannot equal -6. Completely irrelevant. Because if x has to be greater than or equal to -3, that already eliminated any values around -4 or -6. So our domain and interval notation is just -3 inclusive to infinity. That's our domain. Now let's look at this very quickly graphically. All right, square root of x plus 3 over x squared plus 10x plus 24. You have the square root of x plus 3 over x squared plus 10x plus 24. All right, let's look at this function. Where does it start? Look, the last real value here is just graphing on Desmos. -3, 0 inclusive. So on Desmos, if you graph, oh, this is not my On Desmos, if you graph the function, you will see that also when you graph on Desmos, I'd say Desmos is just easier to graph on your calculator. It's faster, it's more accurate, it's easier to see things. That your function has a shape like this, and the last real value is, that's going to be -3, and then on Desmos, that's -3, 0. And so that would translate to the lower bound, but then it continues off until infinity. So if you can interpret the domain graphically, -3 is the lowest x input that's producing a valid y output of 0. All right, now, before we continue, any questions here? All right. Some people are looking like they're losing their energy. What do we need to get them to get their energy back? Do we need to go again? What's that? All right. So here's the deal. You guys are gonna get 2 loaves on Monday. Let's try today. I forgot today, so instead of getting 1 loaf instead of 1 loaf today, you guys get 2 loaves on Monday. Yeah. Set a paper towel down so that. All right. This is going to be a neat trick. So this trick applies to all equations. So anytime you have, look, for this next problem, anytime there's an equal sign, that means you have an equation, right? An equal sign means you have equation. Anytime you have an equation, 2 mathematical relations that equal to each other, it's possible to graph both functions, graph your functions in Desmos. All right, you can graph in Desmos and then find the intercept. Graph in Desmos. Sorry. Graph in, am I in the way, or am I just trying to be small? Okay, I'm sorry. Graph in Desmos and then find the intersection. Find the x value of intersection. Because if these 2 values are equal to each other, if you graph both functions, the point where they intersect is where the y values are equal to each other. You're solving for x, or your input variable, right? You're solving for x or your input variable. So what that means is that the x value of the intersection, that is the solution. So there is a way to do this the way I taught you, and but there's another way to do this in Desmos. Let's try it. All right, I want you all here. Lift your heads up. All right, find the x value of the intersection. Find the x value of the intersection. Sorry, I'm going to try to write that more clearly. Find the x value of the. I'm going to try to write as clear as possible. Guys, come on. Back on task. Find the x value of the intersection and then possible multiple intersections. All right. If there is no intersections, all right, there is no solution, right? No intersections, no solution. Y'all, we can have that. No intersection. No solution. All right, no intersection, no solution. So what are our two equations? We're going to have to use x. We can plug in f of x is, and I want you to follow along with me, is equal to x over x plus 2, and g of x is equal to 4 over x squared minus x minus 6 minus x over x minus 3. Our intersections now, you should follow along, are at negative 1.186, negative 1.457, and 1.686, 0.457. So let me minimize this, do that, scoot this over. All right. Negative 1.186, 1.686. All right, so just drawing this graph. Let's do, one graph has this pattern. The other graph has that pattern. At the intersection, right, our 2 points are negative 1.186, negative 1.457. So I'm just modeling exactly what you interpret on Desmos. 1.686, 0.457. All right. Now, what are your solutions going to be? The x values or the y values? The x values, because if you're solving for k, and we replace k, x is the input value. So if you're solving for x, that's the input values. That's going to be the x value, not the y value. The y values are just what the two functions equal to each other when the x values are the same. So our solutions are k is equal to negative 1.186 and 1.686, and those are our solutions. Now you could do this for this problem, but you could do this for any single problem that has an equal sign. If you had the log base 37 of 34 cubed is equal to the fourth root of 92 over x cubed minus 4x plus a million. Like, you could theoretically put those two equations into Desmos, and if they ever had an intersection, just click on the intersection, that would be your solution. All right, come on. All right, you guys want me to solve this a traditional way as well? Yes? All right, let's do it. So what I need to do is first find the common denominator. So first of all, this becomes k over k plus 2. What is that? What does k squared minus k minus 6 factor into? What does k squared minus k minus 6 factor into? So yeah, k minus 3, k plus 2, minus k over k minus 3. Now what we do here is we get a common denominator. So to get a common denominator, I have to multiply the k plus 2 side by k minus 3 over k minus 3, and then multiply the k minus 3 side by k plus 2 over k plus 2. All right? So k minus 3 times k is k squared minus 3k over k minus 3 k plus 2. That's equal to 4 over k minus 3 times k minus 2. That already has the common denominator. Minus k times k is k squared. K times 2 is 2k. K squared plus 2k over k minus 3 times k plus 2. All right? So now we have our common denominator. Once you have a common denominator, you can cancel it out. That's essentially what I'm doing, is I'm multiplying each side by the common denominator, and so that's how it cancels out. So I end up getting k squared minus 3k is equal to 4. I have to distribute a negative 1 to the k squared and the positive 2k. So 4 minus k squared minus 2k. Now I have to get all my k's on one side because this is a quadratic. Add k squared, subtract 4, add 2k to each side. So on the right side, I also have to add k squared, add 2k, subtract 4. So ultimately get 2k squared minus k minus 4 equals 0. And this does not factor. I can tell you right now, this is not factor. So how do we find the solutions to it? The easiest way is just graph this in Desmos and find when this is equal to, and find the zeros. So Desmos, we can graph in Desmos. This is how you show your work when you use Desmos. You don't write Desmos. You have the equation. You say you graph in Desmos. You draw an interpretation of it. So our equation here is x squared minus x minus 4, okay? And in Desmos, we will see our zeros are negative 1.186 and 1.656, just like before. So we have yep. What's up? Yeah, go ahead. Yeah. So that's plus 2k, right? Oh, so are you talking about yes? Oh yes. So when you had k when you had 4 minus k squared plus 2k, right? So I had 4 minus k squared plus 2k, right? So when I subtract k squared, that's minus k squared. Minus 2k, subtracting positive 2k is minus 2k. So when I have this negative sign right here, I have to distribute the negative sign. So minus positive k squared is minus k squared. Minus 2k is minus 2k. So our zeros are, we have negative 1.186 comma 0 here, and we have 1.6860 here. All right. We're good to go. Any questions before we move on? No? Okay. Oh, let me erase this. Yep. So notice these get you the same answers. Negative 1.186 and 1.686. So I wanted to show you, this way. Why I say the faster way is to graph both equations in Desmos. All right, Jack, let's make sure we get the hood off. Thank you. When you graduate.
What if I drop out?
Just as an incentive for you to not drop out, I won't accept it.
That means I'm graduating.
Yeah, that means you have to graduate and do well for yourself, right? We're good? Okay. Unfreeze. So find the domain, x-intercepts, horizontal and vertical asymptote. So I think it makes sense to start with the vertical asymptote. And the reason why is, come on. Some people make your heads up. The problem is one, so you got to get out. What, like a 10-minute independent practice break? All right. I've set a timer for 10 minutes. How to break a different type of work for 10 minutes. Yep. Interesting. Yes, Matthew, you are not a house. You are a person. Yeah. So the sine of theta is 17 over 20. Let's draw the rectangle. What quadrant are we in? So let's be careful. Let's be careful when we draw. We are in our xy axis. Our angle is in quadrant 1. The triangle is going to look like that. See that? This is the angle right here. What's our opposite? Right? So we can solve for this side is the adjacent. We can solve for the adjacent side with the theorem. Make sure it's in square root terms. So this is going to be the square root of 20 squared minus 17 squared, right? I want you to keep it as 20 squared minus 17 squared. 20 squared minus 17 squared. 111, right? So keep that as the square root of 111, right? And then the cosine is adjacent over hypotenuse, so that'd be root 111 over 20. That's what you put in. Read it when we're done. Yeah. Yes, you may use the restroom. What's up? Oh, you were next. When Lincoln still got right. Everybody go during this 10-minute work. Or not everyone go. Everyone go. No. All right. And you. What's up? Yeah. Yo, we're not engaged when we have the conversation. Oh, that's an intense, passionate conversation. That's not about mathematics. Yeah, D3. Emory's D3 basketball team was beating UNC Chapel Hill. Okay, guys, back on task though. Yep. Yeah, go when at the 3-minute mark. Marco.
Wait. No. I know it's a lie. That's like Mexico. I know it's
Okay. So your degree in the denominator is bigger than your degree in the numerator, right? Which means that you can't divide by first. So nothing, or if you were to do this problem, you couldn't put anything on this side, right? So there's nothing above the division sign with the quotient. There's nothing there. Zero, right? The quotient is zero. The remainder, the entire thing is a remainder because That's one of the ones where probably a lot of people get it right on this. Try. It doesn't make sense. And you look at the hint the first time, like you go through the walkthrough, and then after you look at that hint, yeah. Got it? If you can, I'm serious. Yeah. I cannot because there's 40 seconds before we go back into midterm.
And then look at it, like, boom. Yes or no?
Just put it in. All right. Look at it. One second. Let me turn off that timer. Yeah. Yeah. All right. Heads up. Heads up. Justin, heads up. All right. Heads up. What's up? All right. What? Okay. We got it. We had 10-minute brain break, or not even brain break. Just switching our working activity. We're going back to our midterm practice problems though. All right. So our domain restriction. So our vertical asymptote is a domain restriction, so might as well solve for it first. Because then I can use my domain restrictions to solve for my domain. This is a domain restriction. All right. Also, note that we have the equation in factored form and not factored form. And because we have the equation not in factored form, what we can do is we can see the factors. We can look at the equation in factored form and see that none of the factors cancel out, so there's no holes. So there are no holes because no factors cancel out. No holes, no factors cancel out. So there are no holes and no factors cancel out. So let's solve for vertical asymptotes. How can we solve our vertical asymptotes? What will we do? What do we do to solve for vertical asymptotes? So yeah, and the reason why I'm starting with vertical asymptotes is because the vertical asymptotes are our domain restriction, and you can use the domain restriction to find the domain. Yeah. So we have the factored version and the unfactored version. Right? But here we know there's no holes because no factors cancel out. All right? So guys, make sure we are now transitioned back to our midterm practice sheet and we're working on our midterm problem. No holes, no factors cancel out. So, how do we find our vertical asymptotes? What do we set equal to 0? Our factors in the denominator. Excellent. 2x minus 1 equals 0 and 4x minus 5 equals 0. Add 1 to each side. 2x is equal to 1. Add 5 to each side. 4x is equal to 5. Divide each side by 2. Yep. X is equal to 1/2. X is equal to 5/4. These are our vertical asymptotes. So vertical asymptotes, these are it. These are vertical asymptotes. We had to set what I had to do is we had to set factors in the denominator equal to 0. Denominator equal to 0. That's how we had to do. Then solve for x. All right, so they're vertical asymptotes. From those vertical asymptotes, what can we determine about the domain from the vertical asymptotes? So the vertical asymptotes will inform us about the domain, knowing that there are no holes. No holes or no other domain restrictions. These are only domain restrictions right here. So given these are vertical asymptotes, how will we find our domain? What will we do? Come on, not everyone at once. Right? So what's our lowest bound for our x value? Well, so these are just the values that x can't be. The domain is an interval of everything x can be. All right, that back table, make sure you lift your heads up. Thank you. All right, almost there. Let's go. We go from what? Lowest? So what's the lowest x value that we can have? It goes from negative infinity. So any value less than 1/2, all the way up to what? 1/2. What do we include though? What's next? A union. Then what's next? Well, now we've gone from all values less than 1/2 to 1/2. But we also have values in between 1/2 and 5/4. So how are we 1/2 to 5/4, all in parentheses, union 5/4 to infinity. There we go. Chapow. Chapow. Yes. Well, let's think about it. If you're multiplying by 3, think of it as multiplying the fraction by 3/1, because 3/1 is 3 in fraction form. So that 3 is going to adjust the numerator, right? But your domain restrictions are only coming from the denominator. Your vertical asymptotes and your domain only have come from restricting the denominator. So But that's a good question. All right, so that's the vertical asymptotes, that's the domain. Let's find our horizontal asymptotes, and then we can go for x and y intercepts. For our horizontal asymptote, Matthew. All right, for our horizontal asymptote. All right, the horizontal asymptote when your numerator degree equals your denominator degree. Here, I'll write the whole thing out. Denominator degree. So what's our numerator degree here? Because we have, what's the highest per degree polynomial term? Right? So the highest numerator degree, which is, we have an x squared term in the numerator and an x squared term in the denominator. Right? X squared equals x squared. So this is the case here for this example, that the horizontal asymptote is the ratio of the leading coefficients. So that's close, but we have to distribute that 3 first. Ratio of leading coefficients. So to look at that ratio of leading coefficients, we first have to distribute that 3. And I think the first equation is easier to do. 3 times 3x squared plus 2x minus 8 over 8x squared minus 14x plus 5 is going to simplify to distribute that 3 across the numerator, because that's 3 over 1. That's going to become 9x squared plus 2x minus 8 and over 8x squared minus 14x plus 5. And here, the horizontal asymptote is when x is approaching positive and negative infinity. It's modeling the end behavior and approaching a specific value at the end behavior of the function. And so as x approaches positive infinity, negative infinity, only the highest degree terms become relevant. So this, at a certain point, this is just going to become, what's going to become relevant is 9x squared over 8x squared. And as x approaches infinity, or negative infinity, the horizontal asymptote is going to be y equals 9/8. That's our horizontal asymptote. Now we need to find our x and y intercepts. So when for the x-intercept, yeah. Let me give you guys some time. That's your horizontal asymptote, yeah. For your x-intercept, So think about it as x approaches infinity, 9 infinity squared over 8 infinity squared, the infinities cancel out. And also what those infinities do is they overpower every single other part of the function. Because when you have infinity squared, any of those infinity or constants, they're completely overpowered by the infinity squared. And if you had infinity cubed, that would overpower infinity squared. If you had infinity to the 7, that would overpower infinity to the 6. Right? All right, back table. Come on, let's go. the 3 while we have the numerator? Because that's not, I'm not multiplying the fraction by 3 over 3. I'm multiplying this by 3. And if you rewrite 3 as a fraction, that's 3 over 1. You want the distribute 1 through the denominator, 3 times the numerator. Only gets the numerator. All right, we got that x. All right, are we still getting stuff down? All right, we got that x intercept. At the x-intercept, y is equal to 0. Okay, so let's set the equation so that y is equal to 0. I'm going to have 0 is equal to 3x squared. Oh, so yeah, let's well, actually, this would be easiest when this is factored form. So it's equal to 3 times 3x minus 4 times x minus 2 over 2x minus 1 times 4x minus 5. All right, what happens when I divide each side by 3? What happens when I divide each side by 3? On the right side, the 3's cancel out, and what's 0 divided by 3? 0. So 0 is now equal to 3x minus 4 times x minus 2 over 2x minus 1 times 4x minus 5. Now what happens when I multiply each side by 2x minus 1 times 4x minus 5? 2x minus 1 times 4x minus 5. What? On the right side, what happens on the right side? Yep, 2x minus 1 cancels out with 2x minus 1, 4x minus 5 cancels out with 4x minus 5. And then what's 2x minus 1 times 4x minus 5 times 0? 0. So now I'm just left with the factors in the numerator. 0 is equal to 3x minus 4 times x minus 2. To define my x values, my x-intercepts, I just set these factors equal to 0. I have 3x minus 4 equals 0, and x minus 2 equals 0. Add 4 to each side, 3x is equal to 4. Add 2 to each side, x is equal to 2. Excellent. X is equal to 4/3, and x is equal to 2. So those are our solutions. So our x-intercepts are 2, 0, and 4/3, 0. These are our solutions for our x-intercepts. Now we have our y-intercepts. For our y-intercepts, what's equal to 0? Yeah, for our y-intercepts, x is equal to 0. Notice on the y-axis, the x value is equal to 0. So you have y with f of x is equal to 3 times 0 squared plus 2 times 0 minus 8 over 8 times 0 squared minus 14 times 0 plus 5. Okay? So what happens to 3 times 0 squared plus 2 times 0? 0. So this just becomes y is, in fact, I can just get rid of anything that's multiplied by 0 or 0 squared. So I can get rid of all those 0 squareds. This becomes 3, this simplifies to 3 over 1 times negative 8 over 5. So what's 3 times negative 8? Negative 24 over what? 5. And so that's my solution. My y-intercept is going to be, this is my solution, so my y-intercept is equal to negative 24 fifths. What was that? All right, so here, I want you guys to write this in the way that, so do 0 comma negative 24 fifths. Want to be precise here. All right, so this was a very big problem. All right, this next problem is even bigger. I'm going to show you how complex it is by solving it in real time. All right, I'm going to show you how complex this is. Here's what we do. Find the end behavior. As x approaches negative infinity, and as x approaches infinity, and I'll say, yeah. F of x approaches 15/3 and f of x approaches 15/3, and that's then behavior. So check this out. Let me be serious. I'll do this for real. That is the solution though. This is a rational function where the highest degree is 1, right? And the numerator degree is equal to the denominator degree. So think about it, as x approaches infinity, so conceptually, as the limit as x approaches infinity of f of x is going to be equal to 15 infinity minus 72 over 3 infinity plus 4, where that set negative 72 and that 4 become irrelevant, right? So then this becomes 15 infinity over 3 infinity. Infinities cancel out, and that's going to be equal to 15/3, which is equal to 5. All right. So the end behavior is the limit as x approaches negative infinity of f of x is equal to 5, and the limit as x approaches positive infinity of f of x is equal to 5. Same thing for negative infinity. A negative divided by negative is a positive. You could also just graph this in Desmos. All right. All right. Do infinite practice for the last 6 minutes of class, and then the last 2 minutes to back up.